Now let's consider capacitor and inductor circuits. And we'll just consider a basic one where you just have LC and nothing else. So to make the long story short, and then first we'll look at it in a simplistic way, I think, and we'll try to analyze it a little more in depth. Suppose that you have an inductor here with L, some inductance, and you have a capacitor here with C, some capacitance. And let's say you start with a charge on a capacitor, so you have plus and minus. That would imply that you would have in the beginning some kind of a electric field present here that points from one plate to the other. There's an electric field, but there is no magnetic field in the beginning. So the picture initially is that you have some maximum electric field, and B field through the inductor is 0. And now you flip the switch, and then the charges start to flow. They flow, they flow, they flow. That. At some point, you will reach the following setup. So the switch is now closed, and you reach the following setup where all of the energy stored in the capacitor has been transferred into the inductor, such that now the electric field is 0, and instead the magnetic field is at some maximum value. You will now have some magnetic field here that points through this, along this inductor. And so then what happens is that magnetic energy stored in that magnetic field has nowhere to go, because there is no resistor in the circuit to dissipate the energy, and so that energy is going to flow back into the capacitor. And so you will go that to the third stage where switch is still closed, and now you have a capacitor back, and what will happen is that the energy that was there in the inductor now will be transferred to the capacitor. But as it turns out, the pluses now will be on the bottom, minus top. The magnetic field through the inductor will be 0, but now you will have an electric field that points from plus to minus. You're going to have some maximum electric field here. And then the story will continue, except that now you're going to have, so let's go maybe to the fourth picture. You're going to have let's switch black color. Now you're going to have the charges that will flow through the circuit, and you will lose all of the energy in a capacitor, but that energy will be transferred back to the inductor. And so the picture here would look like this. Well, here's your capacitor. The energy in the electric field is gone. It's been transferred back to the inductor. So here's the inductor, here's the capacitor. And we have some magnetic field, but now in this inductor that points up in this direction. And there is no electric field. And then we wait a little bit, and we end up with a fifth picture, fifth stage, where the energy stored in the inductor is now gone, and instead it has returned back to the capacitor. And now what we have is LC, and we go back to having pluses on the top and minuses on the bottom. And so now I have an electric field here that points down, and I have some maximum electric field here, and I have no magnetic field. The magnetic field is 0. So you get, if you connect a capacitor and an inductor in the circuit, then what you will have here is charges that will flow back and forth, right? If you look at the picture here, what you will have is that the charges, so here you have a plus, and here you have a minus. Obviously, after the energy dissipates from the capacitor, the current will flow like that. And then here in this case, you have a plus on the top, and then you have a minus on the bottom. So the next step from here would be to see that the charges would flow like that, and so you'd have the current that flows in this direction. And of course, if you go back to the first circuit here, after you close the switch, you would see that the charges would have to flow like that in this direction from plus to minus. In other words, if you have an inductor and you have a capacitor, And if you start with a setup where the capacitor is charged, so you have plus, plus, minus, and minus, then you're going to end up with an alternating current where the current flows back and forth. So I will be the alternating current. Now, the only equation, if you're in 1202 class, then the only equation you're responsible for is the equation for the frequency of the oscillation, and that frequency is 1 over 2 pi square root of LC. But where was it? I think it was just LC. 1 over 2 pi square root of LC, where L is the inductance and C is the capacitance. All right. So now we can try to go a little deeper and see how is it exactly that you get this AC. I mean, this sort of should make sense. You transfer energy from the capacitor to the inductor and then back from the inductor to the capacitor. Since there is no resistor in the circuit, there is no way for the energy to dissipate through thermal loss. So energy should just switch back and forth, should rotate from one device to the other. And that should do, but you can try to go a little deeper and you can try to analyze this in terms of the movement of charges. So suppose that you have a, here's the switch is open, and then here's your capacitor, and here's your inductor. Started with pluses, minuses, and there's your picture in the beginning. So then you would have some electric field that points down. You start with some electric field E. There's no magnetic field B at all, and there is no current. And then you flip the switch, and once you flip the switch here, you will see that the current flows, and the current will flow in this direction. Although we can only consider conventional currents here, and so the current will flow like that to the other plate. But this current would be increasing. Would be an increasing current, and if the current is increasing through this inductor here, then the inductor will start to oppose that change, and so the inductor will work as a brake, in the sense that it will slow down the increasing current a little. And while that's happening, the magnetic field through this solenoid is going to be increasing as well. So there's going to be the magnetic field that increases. Note that there would be, and this would be the magnetic field that is set up by this current I here. But at the same time, you would have an opposing magnetic field through this solenoid that would point in the opposite direction. So you'd also have this B opposing green field that would be resisting the change of the magnetic flux through the solenoid. And so the charges would flow, and all right, so then at some point you're going to reach a state where you still have some charges here, but you will have some maximum, the current has increased and it's reached its maximum, right? So you're going to have a solenoid here. You will still have a magnetic field, that is set up by this current I that flows out of the capacitor. But, and let's put some charges here. So you have some charges here. But now this current reached this maximum, so it has a certain maximum value. And let's say that for that infinitesimally small period of time, this I is constant. So you'd have I being constant here. And then likewise, this B would have its maximum value here, and it would also be constant for an infinitesimally short period of time. In that case, there would be no opposing magnetic field B, because there would be no green B. I'm going to put and cross this out, because at this stage, your blue magnetic field would be at its maximum constant value. Although it wouldn't last too long. So we get to that stage, and then you move past that stage. So I'm going to draw this here where you have this capacitor, and you would still have some charges on this capacitor. So I'm still going to put some plus and some minus here, but now the current that flows out of this capacitor is decreasing. Now you have I that decreases, decreasing I. And that implies that the magnetic field, blue magnetic field, set up by this white current here, is also decreasing, while the charges continue to flow to the other side. that would imply that since the blue field through this solenoid is decreasing, that would imply that the solenoid will oppose that change, and so it's going to set up its own magnetic field that points in the same direction as the blue one, and so you're going to have the solenoid, well, supplementing for the loss. And that blue field is not going to be constant, but it is going to be increasing to supplement for the decreasing blue field B, and that would imply that this B, as it increases here, would now push the charges. And so you're going to end up with this increasing B field here is now going to cause this solenoid, this inductor, to help push charges. And so at some point you will reach a state where you have zero charge on the capacitor. But at that stage, you have no charge here anymore. The current has just died out. And so the blue field here has just died out. At this point, this green field is still present there because it's still trying to supplement for the loss. So the blue field is gone, the green field is trying to supplement for that loss of the blue field. So this blue field here is still trying to increase, and that increasing green field still pushes the charges, right? Increasing magnetic field through a loop is going to induce a current, and so you still have, even though this one is dying out, you're going to end up with this opposing current I that still pushes the charges. And so you can move on to the next stage, where in the next stage you would have a capacitor here, and now the inductor on its own, because of the energy that is now packed into this inductor in the form of the green field, pushes down that inductor. As the green field is changing, is going to pack positive charges on the other plate. That will continue for a while until eventually this current here, the green current I, also dies out. And so we end up in this state where we have, oh, that's interesting, look at that. Should be minus here, big minus here. Eventually we will end up in a state where we go to no magnetic field, because this magnetic field has to die out too. The energy that you have in the solenoid runs out at some point. But then all of that is packed into this capacitor where you end up with plus the bottom minus on the top, and now you have these two circuits would be equivalent, except that the capacitor has flipped the charges. Now you'd have the electric field that points up, and then you have no magnetic field and a solenoid, and then at that point this whole process, so the current stops. There's no green current. The green current I is 0. Of course the white current I has already been 0 for a while. So you end up with this picture here, and then you go backwards. It's as if you flip the switch again, and then the charges will flow in the opposite direction, and the story reverses itself. I think this is a little more convoluted picture than if you just look at the energy. Maybe it's easier to understand what's happening here with the with just considering the energy. So if I scroll up here, right, you started with energy packed in the electric field, and then that energy is transferred to the solenoid, and then that energy is stored in the magnetic field of the solenoid, and then that energy is packed from the magnetic field of the solenoid back into the capacitor, and so just the energy goes back and forth, back and forth, back and forth. You end up with a certain frequency and an alternating current I. Solving these problems is trivial, so let's do a problem here where we have solving problems on the level that we're going to do them is rather trivial, but here's a sample problem. And so let's say that we have a solenoid here with a certain inductance and a capacitor with a certain capacitance. So let's say that the capacitance is, let's say we have 10 microfarads, and let's say that the inductor here L is 1 Henry. And the question is, what will be the frequency of the alternating current? Because we know we're going to get from the analysis we just went over, we know that we will get an alternating current AC, and so the question is with what frequency will this current alternate, and that frequency would be 1 over 2 pi times the square root of L times C. Plug in the numbers. 1 over 2 pi times L is 1 times 10 minus 6, square root of this, and this is 1 over equals 50 hertz, and that does it for the frequency. Now if I wanted to find out how long it took for a switch to take place, and I would calculate the period, which is 1 over the frequency. That would be 1 over 50, which is 0.02 of a second, and that's that. So here's a sample problem.